Let's start with something small and concrete, a single short sentence. On the screen we have the words, "The cat sat on the mat." We're going to watch, step by step, how a transformer lets each of these words look around at the others and decide what matters. A computer doesn't see words, it sees numbers. So the very first thing that happens is that every word gets turned into a list of numbers, a vector. Think of each vector as a point in a high-dimensional space, a coordinate that captures something about the word's meaning. We'll draw each of these vectors as a little vertical column of colored cells, warmer for larger values, cooler for smaller ones. Don't worry about the exact numbers. What matters is that similar words end up with similar-looking columns. Here is the core problem attention solves. The word sat on its own is vague. Who sat? The cat. To understand sat properly, the model needs to pull in information from cat. Every word needs a way to gather context from the others. So the question becomes, how should each word decide which other words to pay attention to, and how much? That single question is the whole idea of self-attention. Everything else is machinery to answer it cleanly. The trick is to give each word 3 different roles, 3 different versions of itself. We build these by feeding the word's embedding through 3 separate learned transformations. We call the results the query, the key, and the value. Here's the intuition before any math. The query is what a word is looking for. The key is what a word offers, like a label advertising its content. And the value is the actual information a word will hand over if someone attends to it. A nice analogy is searching a library. Your query is the topic in your head. Each book has a key, the label on its spine. You compare your query to every spine, and where they match you pull the book's value, its contents, off the shelf. Now let's build these 3 roles from the embeddings. Each transformation is just multiplication by a matrix of learned weights. We have 1 weight matrix for queries, 1 for keys, and 1 for values. These matrices are shared across every word in the sentence. Watch what happens for 1 word. We take its embedding column and multiply it by the query matrix, and out comes its query vector. The same embedding times the key matrix gives its key vector, times the value matrix gives its value vector. The crucial point, the same 3 matrices are applied to every word. So the whole sentence, stacked as rows, gets multiplied once by each matrix. In one sweep we produce a query for every word, a key for every word, and a value for every word. Let's give these tables names on screen. This is the Q matrix, every word's query. This is the K matrix, every word's key. And this is the V matrix, every word's value. From now on, all of attention is a conversation between these 3 tables. To keep things clear, let's zoom in and follow just 1 word doing its attention, the word sat. We'll pull out its query vector and set it aside. This single query is sat, asking the rest of the sentence a question. Now sat compares its query against the key of every single word, including itself. The comparison we use is the dot product. 2 vectors that point in similar directions give a large dot product. Vectors that point in different directions give a small or negative one. Let's actually see a dot product happen. We line up the query with the first key, multiply them cell by cell, and add up the results into a single number. That one number is a similarity score, how well sat's question matches that word's label. Now we do the same thing against every other key, one at a time. Query.key for the, for cat, for sat itself, for on, and so on. Each comparison produces 1 raw score. Notice something satisfying. The query for sat lands a high score against cat because the model has learned that a verb wants its subject. It scores low against filler words like the. The dot products are already sniffing out relationships, but raw dot products have a problem. If our vectors are long, meaning high-dimensional, these sums can grow very large, and huge numbers make the next step behave badly. So we tame them with a simple division. We divide every score by the square root of the key dimension. If the vectors have 64 entries, we divide by 8. This keeps the scores in a sensible range no matter how big the vectors get, which stabilizes learning. This is the famous scaling factor in attention. So far we have a row of scaled scores, 1 for each word. Bigger means more relevant to sat, but these are still arbitrary numbers. What we really want is a set of weights that are all positive and add up to 1, like slices of a pie. Then we can treat them as proportions of attention. The tool that turns arbitrary scores into a clean probability distribution is the softmax. It does two things. It makes every number positive by exponentiating, and then it divides by the total so everything sums to exactly 1. Watch it happen. First, each score gets exponentiated, which stretches the big scores far above the small ones. Then we add them all up and divide each by that total. The scores collapse into neat percentages. Here is our attention distribution for SAT, drawn as a probability bar. CAT takes the biggest slice, because the subject matters most to the verb. SAT itself takes a chunk. The filler words each get a thin sliver. This bar is SAT's decision about who to listen to. Let me stress why softmax is more than a normalization trick. Because of the exponential, it sharpens contrasts. A moderately higher score becomes a decisively larger slice. This lets attention be selective, focusing sharply on one or two words rather than smearing evenly across all of them. Now comes the payoff. These weights tell SAT how much of each word to absorb. But absorb what exactly? Not the keys and not the queries. The words hand over their value vectors. Remember, the value is the actual information a word carries. So we compute a weighted average of the value vectors, using the attention weights as the weights. Each value column gets scaled by its slice of the pie. CAT's value is scaled a lot. They's value barely at all. Then we add all the scaled values together. Watch the output vector literally build itself. We start from 0 and slide each weighted value in, one at a time. The CAT contribution dominates and pushes the result strongly in its direction. The tiny contributions nudge it only slightly. And there it is, a brand new vector for SAT. It is no longer just SAT in isolation. It is SAT blended with a heavy dose of CAT, a bit of itself, and traces of the rest. The word now carries its context inside it. Let me say the one sentence that captures the entire mechanism. Self-attention replaces each word's vector with a weighted average of all the word's value vectors, where the weights come from how well that word's query matches each key. That's the whole thing. It's worth pausing on how elegant the division of labor is. The query and key decide where attention goes. The value decides what actually flows. Separating how much from what is exactly what gives attention its flexibility. So far we only did this for the single word SAT, but every word runs the exact same process at the same time. CAT forms its own query and attends to everyone. ON does too. Each word ends up with its own context-mixed output vector. Doing this one word at a time would be slow. The beauty of the design is that we can compute all of it at once with matrix multiplication. Let's see how the whole sentence's scores appear in a single step. Take the entire Q matrix and multiply it by the transpose of the K matrix. Transposing K just means flipping it so its keys line up as columns. The result is one big grid where every entry is a query dotted with a key. This square grid is the score matrix, and it's the heart of attention. Read row by row. Row SAT contains SAT's score against every word. That row is exactly the raw scores we computed by hand a moment ago, now just one line in a bigger picture. Every row is a different word's query against all keys, and every column is a different word's key being compared against all queries. The whole web of word-to-word relationships lives in this one grid. That's why we call it self-attention. The sentence attends to itself. Now we apply the same two cleanup steps we already learned, but to the entire grid at once. First, divide every entry by the square root of the key dimension. This is the scaling that keeps the numbers well behaved. Second, apply softmax, but this time along each row independently. Each row turns into a probability distribution that sums to 1, so every row becomes one word's attention bar, all computed in a single sweep. Let's render this finished grid as a heat map. Bright cells mean strong attention, dark cells mean little. Now the entire sentence's attention pattern is visible in a single glance. This heat map is the picture people usually mean when they talk about attention. Read the map. The bright cell where SAT meets CAT is the verb finding its subject. You can spot other patterns too. The attending to the noun it modifies, words attending to themselves along the diagonal. The grammar of the sentence is quietly glowing in the grid. To finish the computation, we multiply this attention grid by the value matrix. Each row of the grid, a word's weights, mixes the value vectors into that word's output. In one matrix multiply, every word gets its context-enriched vector, exactly what we built by hand for SAT. Let's collect the whole recipe in one line. Softmax of Q times K-transpose, divided by the square root of D, all multiplied by V. Every symbol in that formula is now something you've watched happen. Match queries to keys, scale, normalize, then average the values. Step back and notice what's learned and what isn't. The dot products, the scaling, the softmax, the averaging, none of those have any knobs to tune. The only things the model learns are the three weight matrices that make the queries, keys, and values. That's a profound simplification. Training doesn't learn who attends to whom directly. It learns how to project words into query, key, and value space, and the attention pattern emerges from those projections. Change the projections and the whole heat map reorganizes itself. One real transformer layer runs several of these attention grids in parallel called heads, each free to focus on a different kind of relationship. One head might track subjects and verbs, another might track which adjective belongs to which noun. And we've been watching just one layer stack many layers, and the context-enriched outputs of one become the inputs of the next. Word by word, layer by layer, meaning gets refined until the model genuinely understands how the sentence hangs together. So the next time you hear that attention is the engine behind modern language models, remember what it really is underneath. It is a learned weighted average. Words ask questions with their queries, answer with their keys, and share what they know through their values. We started with 6 lonely word vectors that knew nothing about each other. We end with 6 vectors that each carry the whole sentence's context, woven together by nothing more complicated than a smart weighted average. That's self-attention. If this made it click, subscribe for more visual math.